Ladies and gentlemen, welcome to a fourth video on the Fivefold Sun, this time focusing on section 3 of part 1 of this book. We are on October 5th of the year 2018, and this is about 1 year after the corresponding paper version was filed at the Bibliothèque Nationale de France in Paris in late 2017. Section 3 of part 1 of the Fivefold Sun focuses on an estimation of the rigid rotation in the solar ball, so as to arrive at a translation of the length of the solar cycle in terms of a number of rigid rotations of the ball, as well as translation of the lengths of the rise leg and of the fall leg of the cycle, also in a number of rigid body rotations. The outline of section 3 of part 1 starts with consideration and discussion of the various units that are used in solar physics literature to measure angular velocity in the solar ball and the length of one solar rotation of 360 degrees. Then we turn to an original procedure to arrive at an estimate of the value of rigid body rotation in the Sun. In section 3.3, we review the published values in solar physics literatures for angular velocity of the rigid rotation zone in the Sun, and we will arrive at a certain final estimate for this rotation. Then we will see how this translates in numbers, integral numbers or not, of rigid rotations of the solar ball. In this video lecture, we start in fact with the set of published values for solar rigid rotation that were published in the literature. This is a table that has here the consecutive values of angular velocity in nanohertz from 425 to 437 nanohertz. That is covering the entire span of published estimates for the rigid rotation of the Sun. We have here the values that were reported from 1996 to 2007. Here the values reported in the year 2008, in the year 2009, and this is for only the first half of 2010, because this table was put together in May of 2010, so we do not consider later publications. This table was not updated after 2010, and we are in 2018. What is the set of reported values that have been published as of 2010? Most of the values that were reported are for the value 430 nanohertz. Second most frequent reported value is 433 hertz. We see that those values that are more than 430 nanohertz are much more numerous than those values that were for less than 430 nanohertz. If we now look at a ranking in decreasing order of the 7 values that were reported from 1996 to 2009 in the literature, and these are 437, 436, 435, 433, 430, 429, and 425, at least as far as I could locate such statements in the literature via internet searches and paper literature searches. When you see that after 2000, only 2 values out of this set of 7 values were again reported, either 430 nanohertz or 433 nanohertz. Overall, the value which is reported most frequently is 430 nanohertz, and the second one is 433. We see, however, that the value 433 is reported mostly in papers that are somehow speculative, whereas 430 seems to stem from investigations that are based on actual measurements or on at least attempted such measurements. Also, we see that rates of less than 425 nanohertz or for more than 435 nanohertz are never reported, at least in the search that I was able to perform after the year 2003. This boils down to a value of about 430 nanohertz as a ballpark for the statistically characteristic angular rigid rotation of the solar ball. Now we turn to the original procedure that is also proposed in the Fivefold Sun to arrive at a determination of a rigid body rotation rate in the solar interior. This definition is new, is an innovation. It defines a so-called solar solid body vertex as a certain depth inside the solar ball, where which is located at the least inward radial distance from the solar surface, at which all observed individual latitudinal rotation velocities are the same, angular velocities, of course. So this so-called solar solid body vertex represents a unique transition point in the depth of the solar ball, where a differential rotation, which is seen at the surface and down to a certain depth inward, is first replaced by rigid rotation. And the rigid body rotation that can be defined from the location of this depth is the one common rotation rate value, which is observed, which is inferred by helioseismology at the most outward depth, now looking from the center of the Sun outwards, where the several latitudinal rotation curves in fact merge. This at face value rather theoretical approach is in fact translation in words of the graphical finding that you can glimpse in this figure. This figure is figure 1.3.4.5a in the Fivefold Sun, and it represents a cross-section of the solar ball from the surface at 1.0 radial fraction of the solar radius to half of the solar radius, 0.5 solar radius fraction. And it represents a drawing of the latitudinal rotation curves at the equator, 0 degree, at a latitude of 15 degrees, at a latitude of 30 degrees, at a latitude of 45 degrees, at a latitude of 60 degrees, and at a latitude of 75 degrees. For all but the last latitude, we have a set of three different publications of three different data sets for each latitude from each distinct publication, distinct author. We have only two for 75 degree latitude. What we can see is that there are huge variances between the angular velocities at the various latitudes at the surface of the solar ball. There is not so straightforward fluctuation in angular velocity at each latitude. For instance, for 45 degrees, we see it goes from 410 nanohertz at the solar surface to 415, and then down to 408, and goes sharply up to about 430 or 33 when we reach a singular point where all of these latitudinal curves cross each other and merge into one common rotation rate, which is the sought rigid body rotation rate that prevails in the inner part of the solar ball, namely in the radiative zone, where the radiative nature of energy transfer results in rigid body rotation, whereas in the bulk of this zone, we are in the convective zone of the Sun, where convection results in differential rotation. What we see in this figure is that there is not absolute agreement between the several authors on whether the rigid rotation rate is the same from 0.5 radius fraction to 0.6 or 6.5. Maybe it's rising inward, maybe not. Here it's not. But there is relative agreement between all these authors that there is a common point which is located here. And we can see now in this close-up that the crosses represent the possible locations of the merging point of the latitudinal angular velocity curves, and that their value is slightly above 430 nanohertz, maybe 32, maybe 34, 35. We see that the radial location of this point may be 0.63 radius fraction, or maybe 0.65 radius fraction. So this approach, which is pioneered here in this Fivefold Sun project, leads to pinpoint a certain depth in the Sun where rigid rotation begins. What is remarkable compared to the present state of the art of solar physics is that it is much inward compared to the accepted border between the convective zone and the radiative zone, which is 0.71 radius fraction here. Here we see obviously that there are already huge differences between the various angular velocities at the various latitudes of the convective zone. So we define something which is not the boundary between fully convective zone and something else inward at 0.71, and which is also not what was called in the early 2000s a tachocline. A tachocline being a very thin shell in the Sun where there would be sharp departure in between the rigid rotation rate and differential rotation, which according to several authors would be somewhat below 0.7 radius fraction. Here we are much below, and we are at about 0.63 to 0.66 radius fraction. Anyway, this estimate results in a rigid body rotation rate at the outward region of a rigid rotation zone of about 433 nanohertz. Nevertheless, we remain with the ballpark of 430 nanohertz that results from the various published estimates of rigid body rotation, which include, in contrast to the new approach just sketched above, they include attempts at measurements much more inward towards the solar center and are representative of a larger part of the rigid rotation of the Sun. The solid body vertex marginal rotation, rigid body rotation rate approach will be of interest for us more in part 2, where we will try to explore the interior structure, 3D geometrical structure of the solar ball. Now, on this page of section 3 in part 1 of the Fivefold Sun, we remain with this assumption of a rigid body rotation at 430 nanohertz, and we translate this angular velocity in a number of rigid rotations of the solar ball over the length of the entire solar Schwabe cycle. You see here a number of hypotheses for a Schwabe length of 10.625 years down to a Schwabe length of 10.60 years, with a central assumption of 10.615 years as retained at the end of the previous section of this book in the preceding video lecture. And we see that in this case the number of rigid body rotations is 144.1. For 10.61 years, the number of rigid body rotations is exactly 144. So within margins of error on either the actual value of the rigid body rotation rate in the Sun or on the actual central value of the length of the overall Schwabe cycle, we will find more or less 444 rotations, rigid body rotations across the cycle, maybe 144.1, maybe somewhat less, maybe somewhat more. For longer cycle lengths than 10.625 years, we begin to have cycle lengths in numbers of rigid body rotations that are larger than 144, that would require that the actual rigid body rotation rate would be less than 430, maybe 429, to arrive at the ballpark of 100, exactly 144 rigid rotations across the central value of the Schwabe cycle. This would be the contrary, obviously, if we contemplated lengths of less than 10.6 years. If we now look at the number of rigid body rotations for the same assumption for the rigid body rotation and for the retained central value of the cycle, we find that these are 55 rotations and 89 rotations, plus or minus up to 0.1 rotation. This depends on the actual ratio between the fall and rise leg length, which, as we saw, is about 106.1, maybe 106.15, from 106.1 to 106.2. These are the central values. So we find a solar cycle of about 144 rigid rotations divided into a rise leg of about 55 rotations and a fall leg of 89 rotations. These are Fibonacci numbers. 144 is the 12th Fibonacci number, F12. 89 the 11th Fibonacci number, and 55 the 10th Fibonacci number, F10. The earliest definition of the recursive relation, which is the Fibonacci sequence, is Fn plus 2 equals Fn plus 1 plus Fn. So you see 144 equals 89 plus 55, and the beautiful property of this number sequence is that as the numbers rise in sequence, 1, 1, 2, 3, 5, 8, 13, etc., up to 144, etc., the ratio between Fn plus 1 and Fn tends to this expression, which is again the ratio between mean and extreme values, or a so-called golden ratio, 1.6180, etc. So we find here the ratio which was also found without going through the numbers of rotations of the Sun. And of course, some of those who are listening to this lecture may think that this is maybe not true. Maybe there is so much uncertainty in the measurements that in fact this exact proportion is probably not verified. But skepticism will maybe increase or decrease when you will consider now the numbers of rigid rotations of the solar ball for the mean value of the solar cycle length. Here we use 11.05. This value was determined in section 1 for the mean length. As stressed in section 1, this value changes sharply over time. Every time a new cycle is added, it has a different length and it changes the historical mean. But we independently will find in part 5 from other approaches based on a long-term reconstruction of the solar cycle at the centennial and millennial scale, that it is a rather accurate estimate of the long-term value of this cycle. Maybe it is 11.06 or 05 as found in part 5. So in this case, we have 60.02 rigid rotations in the rise leg and 89.9 rigid rotations in the fall leg. Within uncertainties, again, these numbers happen to amount to integral numbers of rigid body rotations, 60 and 90. And they are not only integral numbers, as may be suggested for the central value length, i.e. 55 and 89, but this time they are multiples of 10. Moreover, they are also related by a ratio which is remarkable. It is not the mean and extreme ratio, this time 1.618, etc., but it is exactly 1.5, i.e. 90 is half as much as 60, one and a half as much as 60. So this amounts to 149.92 rigid rotations, but may be suggested that it is legitimate to round it to 150. It is also possible, if it should be an integral number of rotation, that it is 149. However, whatever the actual accurate, precise values are, we see that they are challenging us in terms of what might be the underlying physics of such relations between rise lengths and fall lengths. And in the case of the central value length, why it might be 144 rigid rotations of the Sun, 144 being a very special Fibonacci number, as we shall see in the following. Thank you for your attention.